All right, everyone. Moving on with our CFD simulation series. Um, I'm gonna talk today in this video about actually running the case that we built previously in a high-performance computing center. This screen that y'all can see here is the interface with the cluster that I use for running the simulations. And the first thing I've done is that I created this folder called test simulation. And in there, um, we can find our case that we set up previously. So now basically what we got to do is just like run um, some commands so the cluster can actually open Ansys Fluent, read the case, and gather data. So the first thing we gotta do is actually create a new empty file, and I'm gonna call this just job.sh. It's basically a text file, and we're gonna fill this with instructions that the high performance computer will read, and basically just setting up a job script and reading input files for Ansys. So let me close this. And what I'm going to do is I'm just going to copy whatever I already had. So I'm going to copy this. Oops. Nope. Yep. So this is the script that we have for job submission, and this is just saying giving a name to the file. By the way, this system, the cluster system, operates in Slurm. That's SLURM. So depending on what kind of system your high performance computing center has, the syntax is going to be different. Since this is Slurm, this is the syntax for it, and just keep that in mind. This is just um, specifying the name of the cluster that's being used. It's Quana. You can see from that screen over there. Number of nodes, which in our case is one. We're using one node in the computer and using 36 cores in that node. Here we are loading Ansys, and the specific version is 19.3. That's the version that we have available in the cluster. And here is opening Fluent, and I'm not really sure. It's been so long that I've looked at these commands, but I suppose this is like disabling uh, the mesh view. Oh no, sorry. This is actually setting up like it's a 3D simulation, and this is disabling the graphic user interface. Since we are running the simulation as a batch process, we don't need the graphics. This is selecting 36 processing units for the simulation. This is to not display the mesh, if I'm not mistaken. Um, I'm not really sure what this is. And this is to read an input file. And this is what we're going to be doing next. Let me save this. So for an input file, um, it's going to be different depending on your particular needs and what kind of cases you're running, if it's a static simulation, if it's a transient simulation, if you are changing boundary conditions between runs, and if you are reading data, or well, whatever you're doing, your input file is going to be different. I'm going to show you what an input file would be for a steady simulation, because that's what we're going to be focusing on in this video. I'm going to write down, it's going to be called input file dot. I'm going to start as a text file, and then I'm going to change that to an input file, just because it's easier to, just to edit the text file and then change the name. So once again, grab, um, I'm gonna grab the, this file that I had here, and I'll have to change a few things. Just copied it there, and I'm gonna change the name of the case file, because this is not really what we have here. I'm gonna change it to test sim AOA 0.cas, and this is initializing the flow, and here I'm giving Fluent the instruction to iterate 500 times, and this is the instruction. This is compatible to the steady state simulation. Um, so from looking at this, you can tell that this is a steady state simulation. And here I'm going to change this name. This is going to be test, test sim AOA 0. This is saying that it's a 0-degree angle of attack. And this is not essential. Just to be sure, I'm putting I'm putting it there. And here, let me see. This is, oh, I gotta change this velocity as well. 62. This is changing. So what's happening here is that the input file is instructing Ansys to read the case, initialize the flow, iterate 500 times, um, noting that it's not, if the convergence criteria is met before 500, it's not actually gonna iterate 500 times. So it's not really a problem to have this big number of iterations in the first run. After it's done with that, um, either if the convergence criteria is met, or if the iterations go until 500, it's going to write the data in a dat file, and well, later on this is what we're going to use for post-processing. After this first case is run, we're going to change boundary conditions, because um, we want to solve different cases with different angles of attack, and this one corresponds to 1-degree angle of attack. So this is cosine of 1, and this is sine of 1, and we're going to repeat that throughout all the angles that we want. In this case, up to 12 degrees angle of attack. So this is going to be tedious. All I'm going to do, I'm just going to change all of these, just change the names, and I'm going to stop the recording for a little bit, and I'll be back later. Okay, so I've changed all the names here. I changed the velocity magnitude as well, to just to match what we had defined previously in our case. And we'll be running from 0 to 12 degrees in this case. It does not mean that we're gonna attain convergence in all of the cases, but later on we'll be able to detect where the simulation, well, the steady simulation stops converging. And that would be the topic for the next video, which would be to run transient simulations using the same the same batch mode technique. So I went on and saved this. So now we're gonna actually just change the name of the file so that Ansys can detect it as an input file. And this is not a problem. You can still open it and read it as a text. The only thing that changed is the extension of the file. So now um, we have to actually go here in the command prompt and change the directory to whatever the directory name is. In our case, it's test simulation. So I'm gonna go on and change the location to there, and I'm gonna submit the job. And we do that with a sbatch command, sbatch job.sh, and a job ID number is going to be assigned to that. And well, since this cluster is used by many users, sometimes your job gets in the queue, so you gotta wait until some resources are allocated for it. And the way you can check for, check the job status is with the saccount command, sact, saccount dash j, and the job ID number, which in this case is 1935678. And we are lucky today. You can see here that it's actually already running. And you can see here it's 36 allocated CPUs, so everything looks fine. I'm gonna go on and refresh my folder, and now you can see that there are um, a few files popped up here. This would be the whatever, well, the one that has E in the extension is an error file, but this is not a bad thing. It's just something that, sometimes it is a bad thing because you're gonna get errors here and the simulation is gonna stop. But in this case, it's just giving you like a standard information that the cleanup script file is whatever. And this is the important file to, so you can keep track of the simulation status as it goes. So if you look at this, this is actually what shows up uh, in an interactive session with Ansys Fluent. So you see here that it's giving that standard message, mixed cells and cell partitions, saying something about the mesh. And this is what actually shows up in the command prompt. Uh, if you remember, the Ansys Fluent screen usually have that command prompt around here. And if you run a simulation with a graphical user interface where you can see, graphics, obviously, if you run that, you're gonna get all those messages in that command area. And what's happening here is that those messages are actually being shown through this output file. So what I usually do is that I use this to actually see what's happening in the batch simulation. I'm gonna pause the recording and I will come back once I have a good amount of data in that output file so I can explain some of the things to you. Okay, I'm back. I decided that I'm not gonna wait until I get the full set of data. It's gonna take a few hours. So what I'm actually gonna do, what I'm gonna do now is I'm gonna show you how it's looking here with the actual case that we set. you can see that it's been just like um, 6 iterations, and you can see that it's improving. But what I'm gonna do is that I'm gonna show a previous case that I had, which is it's basically the same case. And you can see here that I already have all the data that was generated. And I'm gonna just show the output file here. So as the simulation goes on, let me drag, you're gonna have uh, convergence for your monitored quantities, which in this cases are moment, drag, and lift. And you can actually check that here. For example, you can have um, x velocity, all the residuals. Well, this one hasn't converged yet, but let's see. Well, continuity doesn't converge for this case, but let's say that we drag it and, oh, here, for example, here the continuity has converged, and well, basically all of the residuals have converged in this case. Um, Let me see where the heading is so it's easier to see. Yeah, here. So here we have that all the residuals have converged, and drag has converged, lift has converged, moment hasn't yet, but if we look down here, at some point it converges. Where is it? Yep, here for example. Here it's converged. Moment has converged as well. So what happens is that um, in this particular scenario, which was for an angle of attack of 5 degrees, it's going to write the data and the case, and it's going to move on to the next boundary condition. And this keeps going on and on until all of the boundary conditions are explored. But something that um, should be noticed is that as the angle of attack increases in the simulation, you won't be able to get a steady solution for all the cases. Let's say that the angle of attack reaches a point where you get flow separation, you get a lot of nonlinearities, and you get some sort of fluctuation in the results as a result of those things, of those phenomena. You can see that by um, by whether your steady solution is reached or not. So for example, if we drag this list down and we keep track of the how can I say that of the monitored quantities convergence, for example, drag, lift, you can check here, for example, 10 degrees angle of attack, you still have convergence. And because you can see here that um, not all the iterations were used. Remember, we had 500 maximum number of iterations, and here we get 286. So this means that the convergence criteria was met before the maximum amount of iterations was used. And if we go drag it all the way down again, we're going to see that that doesn't happen anymore. past 10 degrees. So here, for example, the maximum number of iterations was met, which means that the convergence criteria was not met, and you can see that from here. And if you compare, for example, let's look at this moment, drag, and lift for all these lines, you're gonna see that there's an oscillatory behavior, and this means that, well, steady solution will not be found. And so we know that 11 degrees is the highest that we can, I mean, sorry, 10 degrees, which was the previous case, was the maximum angle of attack that we could solve by the steady simulation. Um, so now, of course, 12 degrees will also be the same thing. We will not find convergence in 12 degrees since 11 degrees was the maximum. 12 won't even give good results. So this is gonna bring the next topic of the CFD um, simulation series, which would be how to run transient simulations using this batch mode process. So I'll see you there. Thanks for watching, and I hope this video was helpful. And if you have any suggestions or even corrections, just let me know. Those are very welcome because um, I'm actually still learning as well. And I think if anybody wants to um, chime in and give some feedback, that would be amazing. Thank you, and see you next time. Mm.